Many computational photography applications decompose images into a piecewise smooth base layer and a residual detail layer. In this work, we introduce a new way to construct such decompositions at multiple scales. For example, our decompositions may be used to manipulate detail and tone at different scales in order to increase clarity and add depth to photographs. By smoothing a signal, one can extract the details at a given scale, which can then be manipulated and recombined with the base to yield the result. When performing the smoothing, it is important to avoid blurring of strong edges, since this introduces ringing into the detail layer and may result in halos once the base and the detail are recombined. Over-sharpening of strong edges may also cause artifacts. Thus, neither linear filtering nor hard segmentation is well suited for detail extraction, and in practice, edge-preserving smoothing operators are used. In addition, for a multiscale decomposition, the operator must be able to smooth increasingly larger features, allowing larger scale detail to migrate from the base layer into the detail layer. The bilateral filter is probably the most popular edge-preserving filter in computer graphics. This filter does a good job at filtering small-scale details, but it is not well suited for progressive coarsening of images, which requires filtering the larger scale details as well, while preserving the salient edges. Here you can see that if we increase only the spatial support of the filter, sigma s, some small-scale details simply refuse to go away, and sometimes even reappear. To achieve a more aggressive smoothing, it is necessary to increase the range parameter sigma r as well, but this ultimately causes even some of the stronger edges to become blurry, and yet some small-scale details still remain unfiltered. In the limit, increasing sigma r makes that bilateral filter behave like a linear filter. To summarize, in order to produce progressively coarser images, the bilateral filter tends to blur some of the edges that it is supposed to preserve. This introduces ringing into the detail layer, which can cause halo artifacts to appear when the details are boosted. The multiscale bilateral transform of Fattal et al. Produces a more effective image coarsening, but note that some small-scale details remain even in the coarsest level. It also over-sharpens some of the edges, which can cause thin gradient reversal artifacts when details are strongly enhanced. Yet another alternative is the trilateral filter. It manages to filter out most of the fine-scale details, but introduces various artifacts near strong edges. In this work, we use the weighted least squares framework to perform edge-preserving smoothing. As you can see, this operator is able to progressively coarsen the image without introducing strong blurring, over-sharpening, or any other obvious artifacts. Applying the same operator in an iterative fashion generates coarsened images that tend towards a piecewise constant, which is desirable for some applications. We have implemented a simple tool for manipulating local contrasts at different scales based on our multiscale decomposition. Once the decomposition has been computed, the different detail layers can be manipulated at interactive rates. Note that the manipulation range is very wide. It takes an extreme manipulation to cause artifacts to appear. Manipulating the medium detail layer can add depth to the image, while coarse detail manipulation is closer to a global contrast adjustment. Using the same tool, it is easy to perform detail-preserving high dynamic range compression. We begin by compressing the range using a log curve and then restore detail by manipulating the detail layers. For example, we can achieve a flat image with exaggerated fine-scale contrasts, or aim at a more photographic look by a moderate boosting of all detail layers. Our multiscale decompositions can also be used for image abstraction, where details are suppressed rather than enhanced to achieve a stylized abstract look. Doing this at different scales produces different degrees of abstractions, which may be combined together in a spatially varying manner to provide more detail in areas of interest.